In this lecture, we will introduce the area of mathematics called set theory, encountering operations on sets, Venn diagrams, De Morgan's laws, and the inclusion-exclusion principle. In discrete mathematics, a set is simply defined as a collection of objects. These objects are referred to as elements of the set. It's standard to use uppercase letters to represent sets, and lowercase letters to represent the elements of sets. The simplest way to define a set is to list all its elements. The elements are separated by commas and surrounded by curly brackets, or braces. For example, the set V here is the set containing the letters A, E, I, O, and U. Instead of listing elements within these braces, we can also describe all the elements of the set in words. For example, the set V could also be written as the set of letters which are vowels in English. Especially when describing sets of numbers, we can also define the elements algebraically. The example here says that X is the set of all natural numbers with the property that they are greater than 3. This stylized epsilon symbol stands for the phrase is an element of. For example, we can state in symbols that A is an element of V. Similarly, drawing a line through this symbol represents the phrase is not an element of. For example, we can say that B is not an element of V. The elements of a set are regarded collectively as a general group of objects. In particular, no element can be represented more than once. This means that the set containing A, B, B, C, C, and C is equivalent to the set containing just A, B, and C. In general, repeated elements are ignored. This also means that the order of elements in a set is not important. So the set containing A, B, and C is equivalent to the set containing C, B, and A. A finite set has a finite number of elements, which means it is possible to finish counting the contents of the set. For example, our set V is a finite set because it only has 5 elements. On the other hand, for an infinite set, it is not possible to finish counting all its elements. For example, our set X is an infinite set because we cannot finish counting all the integers greater than 3. A particular class of sets is comprised of the intervals of the real number line. These are sets containing all those real numbers between two endpoints. Special bracket notation can be used to easily describe these intervals. To describe the interval from the number A to a larger number B inclusive, we write the numbers A and B between square brackets. If instead one of the endpoints is not included in the interval, round brackets replace the square brackets. Round brackets are also used if an endpoint approaches infinity or negative infinity. It is convenient to represent these intervals diagrammatically. The closed interval 0, 2 can be drawn as a thick line from 0 to 2 on the number line, with the endpoints filled in to indicate that they are included. This half-open interval 0, 2 no longer includes the number 2, so the endpoint at 2 is marked with an unfilled circle. Similarly, the half-open interval 0, 2, which excludes the number 0, will have an unfilled circle at the 0 endpoint. For the open interval 0, 2, both endpoints are unfilled. Two special named sets are the empty set and the universal set. The empty set, also known as the null set, is the set that has no elements. It can be denoted by a pair of braces with nothing between them, or by a zero or circle with a diagonal line through it. An example which results to the empty set is the set of all real numbers that are less than 0 and greater than 1, since no numbers can satisfy both these properties simultaneously. The universal set is the set containing all possible elements relevant to a particular problem or scenario. We denote it by a cursive capital U. For any given problem, the universal set is normally determined by context. For example, in the case where we are given the set V that contains the English vowels, a suitable universal set could be the set that contains all English letters. A set A is called a subset of another set B if all the elements of A can be found in B. The symbol representing the phrase is a subset of resembles a rounded less than or equal sign, so we can symbolically write that A is a subset of B. Similarly, drawing a line through the symbol allows us to write that A is not a subset of B. For example, given the set whose elements are A, B, C, and D, the set containing just the element A is a subset of the set A. The set containing the elements A, B, and C is also a subset of the set A. Indeed, the set containing the elements A, B, C, and D is a subset of the set A. Note this means that A is a subset of itself. Also, the set containing no elements is trivially a subset of A. In fact, in general, we can say that every set is a subset of itself, and the empty set is a subset of every set. We say that two sets are equal if and only if they have the same elements. To prove that two sets A and B are equal, we must prove both that A is a subset of B and that B is a subset of A. In order to manipulate sets, it is useful to define certain operations on them. The union of two sets is denoted by a small stylized letter U and represents the set of elements found in A or B or both. It can be useful to think of the union as describing the logical concept OR. If an element X is in A union B, then we know that X belongs to A or X belongs to B. Note that this concept of OR is not exclusive, so this could still mean that X belongs to A and to B. The intersection of two sets is denoted by an inverted union symbol and represents the set of elements found in both A and B. We can similarly think of the intersection as describing the logical concept AND. If an element X is in A intersect B, then we know that X belongs to A and X belongs to B. The complement of a set A is denoted by writing A superscript C and is the set of all elements from the universal set that do not belong to A. The complement can also be denoted by writing a bar over the set. The complement describes the logical concept NOT. If an element X is in the complement of A, then X belongs to the universal set, but X does not belong to A. Let's practice applying these operations to the kinds of sets we have seen so far. To find the union of two intervals, sketch each interval separately and include all points covered by either interval. For example, here we can sketch the closed interval 0, 3 in red and the open interval -1, 2 in blue. Then their union is the interval covered by red or blue points, which in this case is the half-open interval -1, 3, excluding -1. To find the intersection of two intervals, sketch each interval separately and include only those points covered by both intervals. For example, here we can again sketch the closed interval 0, 3 in red and the open interval -1, 2 in blue. Their intersection is the interval covered by both red and blue points, which in this case is the half-open interval 0, 2, excluding 2. For an example involving finite sets, consider a situation where the universal set is given by the letters A through H, while set A contains the elements A, B, C, and D, and set B contains the elements C, D, E, and F. To find A union B, we list all elements that belong to either set. This turns out to be the set A, B, C, D, E, and F. To find A intersect B, we list only those elements belonging to both sets. This turns out to be the set containing just C and D. To find the complement of A, we list all elements in U that are not in A. Here, the complement of A is the set E, F, G, H. Similarly, the complement of B is the set A, B, G, H. Notice that the intersection of A and A's complement is the empty set, while the union of A and A's complement is the universal set. This makes sense based on their definitions and is always true in general. A useful way to visualize sets is to represent them pictorially using Venn diagrams. To create a Venn diagram, first draw a large rectangle to represent the universal set. Then within this rectangle, draw circles representing any other sets. Usually these circles will all overlap each other in different parts. We can then write the elements of each set in those sections that belong to the sets that they can be found in. For example, using the sets U, A, and B from the previous example, we can represent them in a Venn diagram like this. Notice that the elements A and B lie in the section only belonging to A, while elements C and D lie in the section that belongs to both A and B. Notice also that the elements G and H don't belong to A nor B, but are still written outside of their circles within the rectangle representing the universal set. Let's see what the operations we defined earlier look like when represented in Venn diagrams. The union of the sets A and B can be represented by shading in both circles. The intersection of the sets A and B can be represented by shading in only the middle region that belongs to both circles. The complement of the set A can be represented by shading everything outside of A within the universal set's rectangle. Also, if A is a subset of B, we can show this by drawing A's circle completely inside B's circle. A special pair of relations known as De Morgan's laws describe how the operations of intersection, union, and complement interact. Specifically, the first law states that the complement of the union of two sets is the intersection of the complements of the individual sets. Similarly, the second law states that the complement of the intersection of two sets is the union of the complements of the individual sets. We can demonstrate these equivalences using Venn diagrams. To sketch the complement of the union of A and B, first shade just the region A union B. Then, to find the complement of this, shade instead all currently unshaded regions. On the other hand, to sketch the intersection of the complements of A and B, we can first shade just the complement of A in red, and just the complement of B in blue. Overlaying these two shaded regions, we can then find their intersection by taking only those regions shaded by both red and blue, that is, the purple region. We can now see that these two Venn diagram representations are equivalent. Let's now also demonstrate the second law using Venn diagrams. To sketch the complement of the intersection of A and B, first shade just the region A intersect B. Then, to find the complement of this, shade instead all currently unshaded regions. On the other hand, to sketch the intersection of the complements of A and B, we can again first shade just the complement of A in red and just the complement of B in blue. Overlaying these two shaded regions, we can then find their union by taking only those regions shaded by red or blue. That is, the red, blue, and purple regions together. We can again now see that these two Venn diagram representations are also equivalent. When dealing with finite sets, it can be useful to refer to their size or cardinality. This is just the number of elements in the set, and the size of a set A is denoted by writing vertical bars on either side of the letter A. For example, the size of the set containing elements 0, 1, and 2 is 3, while the size of the empty set is 0. A useful rule which relates the sizes of sets to their union and intersection is given by something called the inclusion-exclusion principle. This states that given any two sets A and B, the size of A union B is equal to the size of A plus the size of B minus the size of A intersect B. This makes sense, since totaling up the elements of A and B separately would mean that those elements belonging to their intersection are counted twice each. So subtracting the size of their intersection means that every element in A union B is counted once. For example, using our previous example for sets U, A, and B, we can see that the size of A union B is 6, while the size of A plus the size of B gives 8, and subtracting the size of A intersect B again gives 6. We call two non-empty sets disjoint if they do not share any elements. This means that their intersection is empty. In the case that the sets A and B are disjoint, the inclusion-exclusion principle simplifies to the expression that the size of A union B equals the size of A plus the size of B. This is because the term involving A intersect B is 0 in this case. Let's now look at an example which can be solved using a Venn diagram. In this question, 150 music students were surveyed. 43 students said they played piano, 110 played guitar, and 88 played flute. Furthermore, 38 of these students said that they played both piano and guitar, 21 played piano and flute, and 61 played guitar and flute. Finally, 18 of these students played all three instruments. Using this information, we're asked to find how many students played none of the three instruments. Let's draw up a Venn diagram representing the information. Here, the set P represents students who play piano, G represents those who play guitar, and F represents those who play flute. Working from the inside out, we know for sure that 18 students played all three instruments. So we can write the number 18 in the intersection of all three sets here, where the number 18 represents not an element of the sets, but the size of the section it lies in. Next, we know that 38 students played piano and guitar, but of these, 18 also played flute. So the difference of 20 must represent those students who play piano and guitar, but not flute. Similarly, 21 played piano and flute, so 3 played piano and flute, but not guitar. And since 61 played guitar and flute, 43 of these did not play piano. Next, we know that 43 students played piano, so the remaining unnumbered section in set P must be the difference between 43 and the sum of the other sections in P. Since 41 students are already accounted for in the numbered sections of P, there must be 2 students remaining who played piano alone. Similarly, since 110 students played guitar, the difference of 29 must have played guitar alone. And since 88 played flute, the difference of 24 must have played flute alone. Finally, adding up all these numbered sections together gives a total of 139. Since 150 students total were surveyed, we know that the remaining 11 students must lie outside all three sets, and therefore 11 students played none of the three instruments. In summary, we have defined the concept of sets and seen examples of infinite sets in the form of real number intervals, as well as the special sets, the empty set and the universal set. We have encountered the set operations union, intersection, and complement, and seen how they interact via De Morgan's laws. We have also seen how the sizes of the union and intersection of two sets are related via the inclusion-exclusion principle.